And now we are at example C among our examples in testing a hypothesis about a population mean value. And so let's now spend some time reading the wording description of our example C here. And so in this example, we are given a sample of 94 people, gave mean breathing rate of 18.55 breaths per minute and standard deviation 8.24 breaths per minute. At significance level 0.01 is the sample showing strong evidence that mean breathing rate is other than 15 BPM. Again, and BPM here the whole time stands for breaths per minute. And so now that, again, this is a question that's asking us to test a hypothesis, and here is the sample showing strong evidence that mean breathing rate. So mean breathing rate here is going to be our mu. And so let mu here be, again, the mean breathing rate. And so the wording in the question is saying the mean breathing rate is other than 15 BPM or breaths per minute. And so that means we can directly translate that into an algebraic expression. Mu is other than 15. And so in that way, we recognize for ourselves an alternative hypothesis, H1, which says mu is other than 15 simply because this is an inequality statement. So now that we can easily recognize our null hypothesis, H of 0, to be mu equal 15 simply because we have already recognized our H1, and so H of 0 is simply pretty much the same statement here, but replaced the inequality with the equal sign. And so this inequality is a little bit tricky because not equal mu is not equal 15 can be mu is greater than 15, but it can also be less than 15. Two possibilities can happen here. And so in that way, with an alternative hypothesis stating as an inequality like this, we regard to this test as a two-tailed test. And I have to emphasize again that throughout the entire lesson, the entire video lesson about testing a hypothesis here, I am mostly going to focus and emphasize on the steps that take to get the problem solved and skip out a lot of logical details that explains how the steps connect to each other, because those logical details must wait for a higher course in statistics to have a complete full understanding. So here again I am simply going to proceed into the steps, how to get a problem done as a two-tailed test. But there won't be too much explanations of why and how the steps are connected. And so now, our sample mean this time, according to the wording description here, we have a sample mean being 18.55 breaths per minute. And so X bar here is 18.55. From the same sample, we also have standard deviation being 8.24 breaths per minute. And that means now I have lowercase s to be 8.24. And the sample we're using here is at sample size 94, because it says right here a sample of 94 people gave the following information. And so in that way, sample size n equals 94 for our sample. And so with this sample mean that we're currently having, again, I will be able to calculate the t star that is corresponding to our sample mean value that we're currently having. And the math to be done here is 18.5 minus 15, which was the value from the null hypothesis, the value that's being claimed in the null hypothesis. And the difference here is divided by a fractional expression, that is 8.24 divided by the sample square root of the sample size, square root of 94. And so as a clarification, 8.24 is the sample standard deviation, and 94 here is the sample size, but it's square root of sample size in that denominator here. And so again, as a reminder, that t star is calculated with the formula x bar minus the value being claimed in the null hypothesis statement, and divide that by s over square root of n, the sample size. Calculation came out for our t star score here is positive 4.177, and a lot longer, but as I have mentioned so many times, unless being specified otherwise, usually I'll just round my t star score, my t star value, to only 3 decimal places. So here it is, we're looking at positive 4.177. And further, since the test that we're about to do here is a two-tail test, so it is important that we emphasize here. So I'm emphasizing with red ink that our t star is a positive t star. And so now that we know our t star is positive, the next step here is to look at the degrees of freedom for our sample. So degrees of freedom is the sample size minus 1, just like any of the earlier problems we have done. And so here in this case, our sample here being a larger sample, so the degrees of freedom now is 94 minus 1, which gives us 93 as our degrees of freedom for this sample. And so now, after getting the degrees of freedom as well as t star value for our sample, now it is time to calculate the p-value of our current sample. And the p-value here, now we need to take the step here a little more cautiously. So we are going to set up a probability calculation, because that's what p is. It's a probability value. That's what p is short for. So I'm going to fire up a probability calculation to find a probability that among all sample means at size 94 this time, we're looking for the probability where our sample mean is. Now, it is now important that I emphasized earlier that the t-score here is a positive t-score. So because of that, I am going to use the right tail inequality, that meaning greater than or equal, and our sample size value here is 18.55. And so this positive sign of the t-score is responsible for firing up the probability calculation as a right tail. But then in the end, being a two-tail as decided previously, we need to multiply this overall probability by 2, because there are 2 different possibilities. That's for our level, that's the simplest way of thinking. Also, that's the simplest way of explaining why we need to multiply the right tail with 2 here. So again, we use the right tail inequality in our probability calculation due to that positive sign of our t-score. But once we've had that probability formulation set up, make sure we are going to multiply that calculation by 2. And so when it comes to this point, and after successfully setting up our p-value as a probability calculation as following, as indicated here, then we can start imagining that our sample that we're particularly having, being at value 18.55, is on a bell curve, where the center of this bell curve is exactly at 15. So rule of thumb now at this point, after doing 3 different problems, center of this bell curve is always at the value being claimed in the null hypothesis. And this bell curve is the bell curve where we can find any possible value or sample mean value of the random variable capital X bar 94. It's a sample mean at sample size 94. And so our sample itself at 18.55 is obviously somewhere to the right hand side, on the right hand side of this bell curve. And so this probability before the doubling right here is understood as a shading area that's shaded to the right hand side due to that positive sign of the t-score and the right tail inequality here. So it's resulting in an area shaded to the right hand side of where our sample stands. And think about and imagine that doubling this inequality means we're going to have an exact duplicate and symmetric area like this on the other side of our current bell curve. And so we're going to find the doubling of this shading area, and that's the picture of this, 2 times the probability. And so now we can easily calculate this black area as the p-value shaded to the right hand side by calling up the tcdf command, which is available in with the TI-83 and 84 calculators and many other calculators outside of the TI-83 and 84. And on the calculator of mine right here, which is the most recent release of the TI-84 calculator, then we can go second variables, scroll down to tcdf, hit enter. And so now one more time, looking back at the area that we're looking for, that we're calculating here, then this area has a low end, has a definite low end being at 18.55 and an indefinite high end, upper end. But unfortunately, this tcdf program will only take t value, and that's the whole reason why we calculated this t star, because this t star is the corresponding t value for our sample mean 18.55. So in my calculator, now the lower end, I am going to enter 4.177. And the upper end is, of course, infinite. It's an indefinite upper end, so I am going to enter 1E99. The degrees of freedom for our sample is 93. So that's what I'm entering, and now I'm going to hit enter a few times. So now similarly for TI-83 calculators or some early TI-84 calculators, after calling the tcdf command from second variables, then instead of seeing a menu like before, we will see the command, the tcdf command, being directly printed on the home screen as seen here. And so we must manually type in the low end and the upper end and the degrees of freedom of our sample into this problem. But same rule, the tcdf command only takes low end and high end as t scores, as t values. So low end in our case is 4.177 positive and with a comma. And now the high end is 1E99. That's how the calculator here, the TI-83 and 84 calculator, can understand as an infinite upper end here, or an infinite end. And then now we're going to hit another comma and with the degrees of freedom 93, and close the parentheses. And so now both versions of the calculator should be able to land into the final answer. And so generally, when we firing up or calling up that TCDF program from a calculator, very likely that it will ask for low end first. So in this case, our low end, instead of 18.55, we're going to enter the corresponding t-score that we have calculated. High end or upper end is indefinite. So I'm going to leave that 1E99. And the degrees of freedom of the sample here is at 93. And so we close that. But then don't forget that even though we have found the answer, we have seen the answer of this after we ran this TCDF program on the calculator screen here, but we need to multiply that answer by 2 right there. So this is a 2 time, and all that answer there will give me our final p-value. And so let me now switch back to my calculator screen. And so the exact same answer here that came right out from the TCDF command, I am going to multiply that answer, which is this current value right here, multiply that by 2. And so our final answer here is the following, 6.65728 with and a lot longer with an e minus 5. So that means our final p-value, in the way how the calculator is written, it means we're looking at 0.000665728.199, and a lot longer, because the calculator wrote this value as a 6.65728.199 times 10 to the minus 5. That's what the computer was expressing, the calculator was expressing, but we understand that as this lengthy decimal right here. And so, as usual, I am going to round this final p-value into 4 decimal places, unless being specified otherwise. And so here it is, our final p-value is a 0.0001. So this final p-value is after we double the result which came out from our TCDF program. And so now that we have calculated our final p-value to be 0.0001, the only thing now is that be aware that this final p-value is a two-tail p-value. So now we are going to compare this final p-value with our significance level being given in the problem. And we're interested in finding out whether 0.0001 is less than the significance level given in the problem or greater than. And so back to the wording of the problem itself. At significance level 0.01. So here we are given a significance level 0.01. So now we are going to compare this final p-value with the given significance level at 0.01. And the comparison now directly shows that our final p-value is well below 0.01, the significance level. And that is now enough to say that the sample we have as an x bar, as a sample mean, is unlikely. Meaning, if we accept this claim, then it is unlikely to have a sample being at this value. And that's leading to a further conclusion saying that x bar that we have here is showing, or itself is a strong evidence. And strong evidence to ultimately to lead us to reject H sub 0, the null hypothesis that claims mu equals 15. Or we can also say we have X bar is a strong evidence for us to support H1, the alternative hypothesis. And the question of our testing hypothesis problem is ultimately a yes or no question. Again, is the sample showing strong evidence? And so just now, apparently, we have proven that X bar as the sample is showing strong evidence. And so ultimately, the answer to this question as a yes or no, it is yes, because we had strong evidence. Now allow me to make another final remark here about this T-star score, because I earlier emphasized that this T-score we've had in this problem was a positive T-score. So the remark I would like to say now is that if the T-star that we found here was negative, and I put this line in red ink right here to emphasize how important that is. So we had our T-score to be positive, that's for sure, but I'm saying that if T-score was negative, so for example, if for any reason that we calculated our T-score to be a negative value for negative 4.177, for example, even though it of course it didn't happen in our problem, but if that was the case, when we proceeded to our p-value calculation, then as usual, we will fire up the probability calculation, looking for sample mean at size 94. But this time, if it was a negative t-score, then we're going to switch the inequality to less than or equal. And again, the sample mean value is placed here. And of course, this overall probability is to be multiplied by 2 due to the fact that this is in the end a two-tail test. And that's the general way of how we handle a two-tail test. So sometimes when we are doing a two-tail test, we have to fire up a left tail inequality and double that probability because the t-score we have calculated was a negative. Or sometimes, just like anyone have seen in our actual problem here, then when the t-score was positive, then we went ahead and set up that probability calculation as a right tail probability calculation and double that final probability. And so now let's quickly look at a different example problem right here, example D. But for this one right here, after viewing 3 different examples before this one, then anyone viewing the video up to this point should have had a lot of experience. And so allow me to really pick up the pace here. So first of all, quickly reading the wording description right here, then we notice that this sample is exactly the same sample that was used in part A, in example A and example B. So I don't have to highlight too much information here any further. So at significance level 0.001 is the sample showing strong evidence that mean breeding rate. So I'll get straight into the testing hypothesis question here. We want to show that mean breeding rate, which is apparently, in this case, we call that our mu value. We want to prove that mean breeding rate is higher than 17 breaths per minute. And so, again, that means we recognized our H1 hypothesis, saying that mu as for mean breathing rate is higher than 17. And so, again, we can now quickly find out that our H sub 0, the null hypothesis, must be saying that mu equals 17. And so now 17 here is a value that we call the claim value in the null hypothesis. And this problem, similar to some of the video we have seen earlier, in our experience up to this point, we can easily decide that the test we are about to do for this problem is a right tail test. That's the test we are about to proceed into. And so just as usual, I am going to quickly sketch down the sampling information. So sample mean x bar is 17.44. Sample standard deviation is 7.99. And we are using the sample being as large as 71. That's for sample size. So I can quickly bring back what's on the computer screen so anyone can be convinced about that. This is sample size, this is sample mean, and this is sample standard deviation, as it says right here, standard deviation being 7.99. And so just as usual, I am going to, as my first step, calculate my t star value. And so from where our sample mean value is, being 17.44, I am going to subtract that sample mean value with the value that's claimed in the null hypothesis. And that difference there is divided by 7.99 over square root of 71. So just the exact same setup we have been using throughout all examples so far. So in this problem, allowed me to skip reminding anyone about the t star formula. Calculation of mine came out 0.464. So that's, and it's a positive value, making it consistent with the test here is currently decided to proceed as a right tail test. And so that's our t star being positive 0.464. The degrees of freedom is 70 because it's 71 minus 1. And so now we are going to proceed the problem as a right tail test. So very similar work that we have done back in some of the earlier examples. This p-value here is set up as a probability calculation where we're looking for sample mean at size 71 is having value greater than or equal to 17.44. But this time the problem is simply a right tail test. So there's no need to double this probability, as we have seen in some of the earlier problem where we had a two-tail test. And so now this probability calculation is graphically represented as the area on the bell curve with center at 17 and shaded to the right hand side of 17.44. So this is what this black area shaded to the right hand side of 17.44. Our sample mean value on this bell curve is the graphical description of this probability problem. We will then calculate this area by running the tcdf command. And the tcdf command, so on my computer screen right here, I'm going to go second variables and look for tcdf again. And the low end, I am going to provide, instead of the actual sample mean value, we have to enter t-score 0.464 for low end. And again, since we're having an indefinite upper end of our interval here, then this upper end right here, we're going to have to leave it as 1E99 as it's already been here on the screen. I am going to enter the 70 for degrees of freedom and hit enter a few times. And now with a final enter right here that we come up with our final p-value here. And so again, on my writing board, generally speaking, TCDF command will take lower value first, lower end of the interval of the t interval. So 0.464 is what we gave it. And upper end, we have to leave 1E99 as it was an indefinite upper end. And we were working with degrees of freedom, 70. And the result that came out from this TCDF command is our p-value. So we saw that on the computer screen being 0.322, 0.043, and a lot longer. But just as usual, I am going to round final p-value to 4 decimals, which is in this case forcing us down to only 3 decimals. So p-value equals 0.322. And now that we know our final p-value is 0.322, then the next step is to compare that current p-value that we've found with significance level given in the problem. So quickly looking back at the problem itself right here, we're looking at significance level 0.001. And so with 0.001 being our significance level, then this time, so the real big thing that I would like to emphasize in this entire problem is that the final p-value here, unlike any other problems we have seen, the p-value here is greater than the significance level. Admittedly, that the rest of the structures of the problem, including the steps and the way how the calculations were done, remains exactly the same. But so now when it comes to final p-value being greater than the significance level, now it leads to our conclusion saying as following: the sample we have is not unlikely. Another way of saying is nothing unlikely. About the sample we have, if we accepted that claim. And that's now leading to a further conclusion, now saying that the sample that we're using here is not showing, or itself not strong evidence. So having a sample like this, we didn't have strong evidence. And admittedly, as I have mentioned so many times, here we mostly emphasize on the steps and be able to make some brief interpretation of the final result. What this means in terms of the final p-value is greater than the significance level. But unfortunately, if anyone is looking for better detailed explanation about why having this comparison leads to nothing unlikely, and why nothing unlikely is leading to not having strong evidence, all that logical reasoning must wait for a higher course in statistics. But now, as we're not having strong evidence, or as x bar itself, the sample itself, is not strong evidence, then obviously, just like how I have pointed out in the general lecture, then what leads further is that we failed. This test right here obviously showed that we failed. This sample failed to reject h sub 0. So meaning we haven't found anything wrong about this claim like that. So that's what it means by we failed to reject h sub 0. Or we can also say that we failed to support h1 on the other hand. And so back to the question itself, apparently it's a yes or no question. Is the sample showing strong evidence? And we did not have strong evidence as indicated here. So in that way, we're saying no as the final answer to this overall question.